Good evening, everybody. My name is Eric, and I'm one of the organizers of the AppliedAI meetup, and I'm going to be your host this evening. The other organizers are Jan, Daniel, and Justin. If you're new to this meetup, I would like to extend a very warm welcome to you. If you've joined us in the past, thank you and welcome. Our meetups are always on the first Thursday of every month. So that means our next meetup is going to be on September 2nd. The topic then will be using AI to proactively improve code quality and security. So we hope you'll be able to join us on September 2nd. Please invite a friend along. And we have a link for that meetup in the chat. We also have an AI podcast called Conversations on Applied AI. And this podcast is hosted by Justin, one of our co-organizers. Please give it a listen when you get a chance. Also, if you know of someone who would make a good guest on the podcast, please feel free to reach out to me or Justin. There is a link for the podcast in the chat as well. So on to our presenters this evening. Our presenters are Sona and Jeff. Both Sona and Jeff are experienced data scientists. So I would say we're in very good company tonight. This evening, we're going to get an introduction to PyTorch and computer vision. And then Sona and Jeff will share some approaches to solve image classification using deep learning. And then they'll tie those concepts together with a demo on how to use PyTorch for computer vision applications. And then as Sona and Jeff just mentioned earlier, they're open to taking questions as the presentation goes. So without much further ado, I'd like to present Sona and Jeff. Please take it away.
Hey, thank you.
You're welcome.
I am going to try and present my screen, share screen here.
Yep.
So, let me know when you can see my screen. It's just my black monitor at the moment.
Yes.
So
there we go. Yes.
Hey, thank you. Thanks everybody, and thanks to everybody who makes AppliedAI possible for inviting us to make this presentation today. And just a little bit on ourselves. So I'll let Jeff go first. Jeff, you're on mute. Okay.
Yeah. So I'm currently working as a software development engineer at Veritas. We do a lot of different things there, but primarily I like building things, and I have a good mathematical background. So I like to, when I can, find ways to use applied math or statistics to address problems. Was that enough introduction?
Okay. Hey, so I'll go next. I am Sona Mangan. Currently, I'm working as a data scientist at Castle Lake LP, which is a private equity firm. Before this, like we just talked about earlier, Jeff and I worked together at Veritas Technologies, and I am when I'm not geeking out, I like reading. I like long drives, and yeah, I'm a mother to 3 girls, and I am second act here. Like I went back to school, took a degree, and been in the workforce only for 7 years. So that's me. And just a disclaimer before we go ahead, like I'm not an expert either in PyTorch or computer vision. I'm here to learn just like you. So that's a little bit on the agenda for today. We are going to go over what is computer vision, an intro to computer vision, then why computer vision is a hard problem. And a refresher on deep learning. This is an AppliedAI meetup group. I'm sure you have listened to several talks on deep learning. So I'm not going to go very deep, pun intended. So in there, but I will just go over what is deep learning, and then I'll introduce PyTorch, and then we'll talk a little bit about the data set that we are demoing today, the architecture that architecture for making that neural network work, and what were some of the challenges in processing that data and fine-tuning the network. Okay, take it off. And so this is a definition for computer vision that I took off Wikipedia. It says it's interdisciplinary scientific field that deals with how computers can gain a high-level understanding from digital images or videos. It seeks to understand and automate tasks that human visual system can do. So the key here is the goal is to do or mimic human vision. And from the perspective of AI, where computer vision comes in, is like you want to get some meaningful information from all those digital images out there, the videos, the other visual inputs. And for a system or a human to be able to take an action based on some recommendation or some kind of inference that can be made from that, from computer vision. So before we go into how a computer actually sees an image, let's look at how a person sees an image. What actually happens is light comes in, it reflects off the object, it travels in a straight line, it goes into our eye. There are photoreceptors on our retina, and these transform that light into electrical signals. The next thing that happens is these signals travel through the optic nerve to our brain, and the brain processes these signals to create an image. So the key is the brain processes these signals to create an image. And in that processing, there's a lot of interpretation happening as well. And about more than half of our brain is involved in this visual processing. And it is key to our survival, our navigation, how we communicate. And there is about 540 million years of evolution that is actually behind this computer vision. And the vision, it starts with our eyes, but what's actually happening is it's happening in our heads, in our brains. And this is what we are trying to mimic with an algorithm. So how does a computer see an image? So this is our classic 8 from the endless data set. So it's black and white. So this is a grayscale image. It sees it as like, this is a 28. Yeah, this is a 28 by 28 pixel image. The scaling is from 0 to 255, where 0 is black and 255 is bright white. And this is the so these are pixels, right? The computer sees images as pixels. This one to the left corner is a black, it's represented as 0, and here you have a white, which is the 8 and 19th. It's in that 8, 19th position that for X and Y axis, and it's 255. So this is how a computer sees an image, not at all like how you and I see an image. What if this is color? So if it's color, okay, here I am only going to be talking about the RVP scale. So if it's color, it's going to be seen as in different shades, or let's say different different shades of red, different intensities of red, green, and okay, red, green, and blue. Sorry about that. Yeah. So let's talk about the leftmost pixel, the 0 at the 0, 0 position. It's 11 for intensity of green, blue, 102 for blue, and Okay, I'm getting my letters confused here. So there's red, there's green, there is red, there's green, and there's, all right. So this is how a computer actually sees, this is how a computer actually sees a color picture. Now, this is very different from how we would see it. And when we see this, we see this motorcycle, we are making so many interpretations here. Is this a new motorcycle? Is this one from like a long period ago? Where is it? It's in a Rocky Mountain area. There's so much that goes into in our brain trying to interpret this image. And we don't just classify it as motorcycle, right? There's so much other peripheral information that we are getting from this picture. Now, let's think about why this is hard for a computer. I'm gonna to look at the philosophical side of it. Okay, you see this image. What are you getting? There is like 3 mirrors here. There's a person standing on the scale, and there's President Obama who's putting his, he's pressing his foot on that scale, and we know how physics works. We know what the interpretation is, what's going to happen here. We already find the image funny before this person has chalk on his face, right? So this is how we interpret. This is our cognitive senses going in and interpreting this image. So this I've taken from actually Andrej Karpathy's website, where he talks about why computer vision is hard. And I have a link to it at the end of our slides as a reference. And so would a computer be able to actually say this picture is funny, or add funny label to this picture? How many images does it have to see? How is it going to interpret this? Will it think that there are more people in this room than there are because there are 3 mirrors here? That's a hard problem, right? Now, apart from just this interpretation, what else can be hard? Just how the images are. Sometimes it's lighting, the illumination variability that can make a computer tag two pictures of exactly the same thing, or the same person, or the same object as 2 different objects. Computer predicts it wrongly because of how the lighting is. Sometimes it is the class variability. Think about this. This is a smaller dog, and this is a bigger dog. And imagine this is with like so many different animals and so many different classes of animals, and variability within each one of these classes. And what is important? So what all does a person who is feeding data into the algorithm need to keep in mind so that there is high accuracy in prediction? And again, think of a child being shown pictures of cats in exactly the same position, and different cats, but exactly in the same position. And then you show one of these pictures in a different pose. Will the child, even a 5-year-old child, would say it's a cat, right? But if you do that with a computer, you show cat sitting up straight, and then suddenly you show a picture like this or like this. Would it be able to predict that this is a cat? That's going to be hard. That's a hard problem. You need to be able to feed the computer pictures in different poses for it to actually go ahead and say that this is a cat as well. And then occursion. And in our real life images, okay, this is something that Jeff is going to allude to a little bit with the data set that he worked with for the demo. So occursion is a really big problem. Not all images are perfectly in place, because images are not like, this is not your passport photograph, right? This is not a photograph that is taken only for the purpose of classifying it as belonging to, assigning a particular label on it. You have to take an image from a real world scenario, and then you have to make a prediction or an interpretation based on that. So this is why computer vision is a hard problem. And one of the ways in which, one of the ways in which it can be made easy is by pre-processing the data. So pre-processing the data is not just to augment the data, but also it can be to reduce the complexity of the data. There can be a lot of unnecessary information in the images. For example, not every image, not every problem that needs to be solved needs the images to be in color scale. And like we saw earlier, for color scale, there are 3 channels out there: the red, the blue, and the green. But you can convert it to grayscale, and that reduces a lot of space complexity, and in terms of computing power, computing complexity as well. And then some of the algorithms need us to standardize images, right? For like previously, CNN required, CNN is convolutional neural networks. They require the algorithms to be of a the images to be of a standard size to get to be fed into the algorithm. So, and apart from this, sometimes it is you need to standardize the image also for the for interpretation purpose, right? So think about a tiny poodle and a huge dog, and a larger dog like a German Shepherd, or one of the larger breeds of dogs, and then you are trying to say these are 2 different classes of dogs. So if the image is not if that scaling is not shown, it will be very difficult for the algorithm to actually pick up that size is important in determining like which class it belongs to. And then another thing that Jeff is going to allude to is why sometimes the rotation is important, flips are important. And then, and it's also sometimes important to detexturize an image before feeding it in an algorithm. This is like one of the talks I went to, a person was sharing that so an algorithm which was trained with a lot of images of different different objects predicted that a gun was a turtle. So the reason was because the handle of the gun had leather that was textured like the back or the shell of a turtle. So these are all things that that a practitioner needs to keep in mind while processing, like getting the data ready to feed into an algorithm. And so feature extraction is an important, especially if you're working with algorithms that are more manual in nature. Feature extraction is very important, and it is something that gives that uniqueness to that image. But a good feature is not something that overfits the image either, right? Because you want it to be generalizable. So it can features can be distinct colors, shapes, edges, image segments, and then you also need to think about what is a good feature. So here the example is a wheel is a good feature if you want to distinguish between a motorcycle and a dog, but it may not be the best feature when you want to try and distinguish a motorcycle from a bicycle. So, so you again, something to think about when you are choosing the images, or when you're feeding different images in and with different labels, is that into an algorithm, is that the features should capture something, some unique or some important type of information about that image. And it is it's almost imperative that you start thinking about Opencv when you think computer vision, because it is a choice of many computer scientists to computer vision scientists to process and to work with visual images. it includes hundreds of algorithms to process, hundreds of computer vision algorithms to process images, and it focuses on real-time image processing. It is Opencv is a library that can be used with many different languages like C++, Python, Java, and others. And you can work even on GPUs with it. And I am gonna talk a little bit more about, like, talking about Opencv is like a ton of the feature engineering is sometimes done with Opencv, because it has all of these nice little functions where you can transform your images, you can resize it, you can maybe make it lighter, darker, you can change its coloring, etc. And so this is what you do, like, a traditional machine learning algorithm, like other than neural networks. What you do is you have the input, you do some feature engineering, you apply it to a classifier with sorry about that. Yeah, a classifier with not as deep deep layers as neural network, and then you get your output, or like you apply it with an algorithm like an SVM, and then you get your output. And then with neural networks, what happens is there is a lot of automatic feature extraction happening. The algorithm itself learns from the image, it learns where the edges are, and it has like it assigns weights to it. It does a lot of that feature learning, and then it classifies it. You don't do it as much outside of the algorithm. And that takes us to a little bit of a refresher on deep learning. So deep learning is a machine learning model that has been inspired by how our human brains are structured, the neurons in our brain. So each computational unit, a neuron, is connected to another neuron in a layered fashion. And when there are multiple layers, that is more than 2 layers, it's called a deep neural network. And deep neural networks are not new. They've been around for a pretty long time, like from the 1950s. But they actually became a powerful way to do machine learnings, because our computational resources, they became more powerful. We have more compute power now, and we are able to store all of these large data sets, and we do have large data sets available to make training possible, which was not the case previously. This is like probably took off a lot after the whole after the internet, after the web, the World Wide Web took off, the internet took off, and then we have so much cloud computing resources and all that. And a little bit on, I think I skipped the slide here. So there are several deep learning architectures, and each of them require a different, the algorithm to be structured slightly differently, and they're all different algorithms. I mean, the basic underlying structure is the same, a little bit different in how they're architected. So the basic, classic one is a perceptron, right, where it all started. It's a single layer neural network. And then you have a fully connected layer, connected neural network, where all the neurons in one layer are connected to the neurons in the next layer. And there is the convolutional neural network, where convolution layers convolve the input, or there's an operation happening here, and then it passes that result to the next layer. This has been pretty effective for working on computer vision problems. And then there are the recurrent neural networks. What happens in the recurrent neural networks is The connections allow memories of the past inputs, which you can see with this little arrow that's turning back inward. And this is used quite a bit with the natural language processing. And there are dropout layers. And what dropout layers do is there are architectures where there are dropout layers. And what this does is that there is randomly some of the neurons are switched off. And it helps in creating a more generalizability to the architecture, to the whole network. And then there is the deconvolutional neural network. And this is mostly used like a reverse engineering, where it is like it generates or reconstructs images. These, like I'm not going to show any more architectures, but these are not the only architectures out there. I'm sure you caught me missing quite a few. But the reason I showed this is that it gives you an intuition about why having a standard library with all the functions will be useful in training and testing models. And like if you look at the history of like artificial intelligence, see that like when ImageNet with the computer vision that challenged, then ImageNet was like Jeffrey Hinton's and team's neural network kind of came out with a higher accuracy than other algorithms at that time. It was a neural network architecture there, right? But think about the amount of coding and the amount of handwritten functions that would have had to go into that particular network to make it possible. But today, with libraries like sklearn, TensorFlow, PyTorch, the adoption of machine learning has been accelerated. Okay? And you don't have to hand code each one of these architectures. And that's important, and that makes it accessible. The whole, the deep learning and machine learning accessible to more people, and it does not turn like I'm not this great C++ programmer. I will not be able to do deep learning. No, it gives it that framework actually makes it accessible and makes it like it's generating new like interest in the field, and it's also making the data scientists and other computer vision experts focus on what matters rather than writing this each and everything again and again and again, and everybody is not doing this. So and standardizing it also means that you can test and it is repeatable. And that takes us to PyTorch. So PyTorch is an open source machine learning framework. It's mainly the application is in computer vision and natural language processing. It's from a historic perspective, it started off as Torch, which is a library which is written in Lua, the programming language. But later, they made a Python version, a C++ version, which had Python as a front end. And now this Torch is not being maintained anymore. It's PyTorch that's being maintained. And primarily, it's developed now and maintained at Facebook. And that's mainly because Salvat Chintala, who is one of the original authors of Torch, moved to Facebook, and they've taken on this project. And computer vision is pretty big at Facebook. And it's got a rich ecosystem of tools and libraries that have been actively developed. There's about 1,600 plus contributors with several downstream projects that have come about from this ecosystem, and a very big community behind this. And some of these tools and libraries which are being developed are very specific for PyTorch, like Torch Vision, Torch Text, Torch Audio. And another very exciting feature about PyTorch, I mean, this is a big feature, that it works on GPUs, so it can process pretty fast, and it's scalable. When you think about PyTorch, what are the core components that make up PyTorch? The basic underlying data structure is a tensor. A tensor is just an n-dimensional data structure. It contains information about, it contains the data, a little bit of information about describing its size, its data type, where it resides, whether it's on a CPU or whether it's going to be on a GPU. It's very, very similar to NumPy, a NumPy array. There are a number of functions and operations that are very similar to what you have in NumPy. And it runs on several accelerators. It started off being able to run only on NVIDIA GPUs, but now it also runs on TPUs. I think there are some graph databases that it runs on, graph structures that it runs on, and then it can be used for scientific computing, machine learning. And the tensors can be, like here I've just shown like how you can move a tensor to a GPU just by adding Cuda to it. And here the fun thing about this is like you can actually write it and test it on your local machine, and then apply the same code on like Collab or one of the places where you have access to the GPU, and the same code should, in theory, should work. So so these are just two things, right? And one of the big things in neural networks is that there is the whole a part of the neural networks where there is the derivative calculation, right, for the back propagation phase of it. So Python actually does this with the PyTorch actually does this with automatic differentiation, and it does it efficiently. And when we're talking about, like, imagine hand coding this is going to be painful, but this happens behind the scenes. You can use that library without having to do all of that by hand. And the other good thing is you don't have to write a ton of structures to keep the bookkeeping that's there. And especially when you're talking about, multiple layers, a neural network with multiple layers, and very large number of images and things like that. The whole bookkeeping is taken care of by PyTorch. So just a little bit more comparing how easy it is. If you work with, like, I think most people who are familiar with NumPy arrays would find it pretty easy to start working with PyTorch. So it's just, just like we would construct 3x2 matrix, we can do the same thing with Torch. You can randomly initiate a matrix. You can get the size. This looks very similar to what we do in NumPy, and then you can do some indexing and get like a particular index. You can do math on the tensors. You can convert, and this is a big thing. You can convert a tensor easily to a NumPy array. You can do, like, you want to bring in some, you want to do some processing with using scikit-learn or one of those libraries. You can do that with NumPy and then convert that to a Torch tensor. And all of that is done pretty fast, does not take up a lot of memory. So it's pretty efficient. And here, I'm just going to give a little bit of an example of how the Torch NN package, or the mostly when we say PyTorch, it is used for neural networks, right? So this is the main package there. It is torch.nn. and how the generally you would construct the class. This way you have, excuse me. You have the constructor where you define the layers, you have the weights, the biases, the convolutions, and all of that. This is a very simple one. And then you would have the feed forward, the function, and then here this one as value as the activation layer, activation for these layers, and then I think the last one is a softmax layer, because there is like I think this was done for ImageNet, and the code not ImageNet. This was not for the MNIST dataset, and that is actually available on our Git repo. And then the next step to a neural network training is, of course, the loss, computing the loss. So again, you see from the NN package, I can bring in this function. And then there is a torch.optim for optimization. Here it takes the Atom optimizer, and there's a learning rate, and this is going through and training the network. It's applying the loss. Yeah, this is the loss back. It's applying the loss backwards through the network's parameters. And then here you have testing it on the test data set and prints out the accuracy. Again, this whole thing, like few lines of code, and you get that done. And this is this is how simple and easy it is with PyTorch. I'm not going to go over like the differences with TensorFlow here, but that's something to think about. And then if you're really interested in the learning a lot more about the insight, the insights, how the actual code behind the scenes in PyTorch works. One really good, really good source is this, the PyTorch internals from this blog. So it's by one of the main contributors to PyTorch. Yeah, I will stop here and let, I've talked quite a bit, and let Jeff take over. And he is going to start with the data set, which is which he used to train like the larger network. And yeah, Jeff.
Okay. So let's see. You want me to just ask you to move to the slides, or?
Yeah. So I have just this one slide, and then I'll let you talk about the architecture and get on and talk as you do the demo.
Okay.
I think at that point, maybe you need to take the screen. Yeah.
All right. And so there's a somewhat, I don't know if simple is the right word, but it's a smaller data set that we could use as an example for transfer learning. So transfer learning is if we take a deep network that's already trained on the similar classification problem, like ImageNet or was it VGG or AlexNet, Inception 3, and so on. They were all trained to distinguish between a large number of image classes. So you can take that trained network and just replace the last classification layer with an untrained one for your image classification, and then just train that last layer. So you don't have to have all the a huge data set. You don't need to have all the computational resources and so on. And it's a good way to learn and play around with some of the functions that your framework might give you. So in our case, it's PyTorch. All right, so it's okay for me to share my screen?
Yes. So I made you a co-host, so you're able to share your screen.
Yep. So
I'm going to stop sharing so that Jeff can start.
And so I'm not sure, I got a new notebook here, so I don't know if the resolution's too good for Zoom. We'll see.
Let's see. Yeah, I can see your screen.
Okay.
Yeah.
So, I'll try to make this one available after. Had a number of things happen that I didn't get as far as I would like, but the work's done. It's just not polished to something I would appreciate. So first, I'm using the Collab Notebook from Google. So they give you a computation environment that's similar to Jupyter Notebook. It has some differences. It has limited disk and RAM. And if you click on here, I haven't tried it, but you can, I think, connect to your own machine with a local runtime. But I have it configured to use the GPU, and sometimes it kicks me out, probably because I'm not paying their $10 a month for the Pro. So here's some notes. I won't go over them, but it says where we got some of our information. So, and why we made some of the trade-offs that it did. And so go over the notebook setup, again, more about the data set. Look at some examples and what the training data set looks like. Briefly talk about reproducibility. Because of the unbalanced classes, so some classes have a lot more training examples and some have hardly any. So we use stratified sampling rather than uniformly random sampling from all the classes as if they were one. And then this goes into some things that, you know, if I talk about them now, might be harder to understand, but we'll go through PyTorch. It uses some concepts like a data set class, and then in order to do batches from your data set, it'll use a data set loader and go over the main loop for training, and then take a simple network and do transfer learning. And I'm not sure that we'll actually run the training, but have the results and then evaluate the model performance. But I can just kick this off once and hopefully we'll get there. If not, we'll still see it. Because I ran it once before. So if we just, this will just run everything while I'm talking. So the first step you want to do is, if you start using, because anyone can use this, right? You just need a web browser and go to collab.research.google.com. Then you go on runtime and go to, see, edit, and then maybe I want notebook settings. I read my own notes. So here, none means you don't have any acceleration, so everything would be on GPU or the CPU. If you have GPU or TPU, then you can move some of your constructs there and use the accelerator. So in order to use the GPU, you'd select this and then hit save, and then it's going to ask you to restart the notebook. So this maybe not so interesting. Just have the imports up above. So it's mostly Torch, the image processing library, matplotlib, so we can plot some images and read them from a zip file. And so in order to plot in a notebook, you use this inline. And then, sorry, I forget what this is. I'd have to double check and look back, but there's some issues with trying to get matplotlib to actually work better with a notebook. So this will download the training and testing data sets. So if you go to that website, you would see that they have a lot of different data sets. These two are cropped ones. So this each image is going to be cropped and centered so that the sign is in the center of the image, and probably between 25 to 50% of the image is actually the sign, because a lot of their signs are triangles. So it's probably more like 25% of the image is the sign then. So I won't go over this too much because of time, but what I did was, because if I save the zip files to Google Drive or someplace else like that, it takes a very long time to read the images, especially if you extract them all to Google Drive. So they're downloaded to this VM and just saved as zip files. So they'll go through and read based on the Python zip file class. Now the part where we need to do some manipulation is here. So once you get an image file from there, we need to know what the type was. So you find out they use some really old format called PPM, which is used in a lot of universities still because it's easier to work with for computer vision. So you open the file and then use the image processing library to open it. And that will spit out some kind of image in memory. And then we need to convert that from that representation to a NumPy array. So this NumPy as array will do that. And then convert the NumPy array to a torch tensor. So I think there's some memory copy going on here, but the torch tensor from a NumPy array, or in the reverse order, they share the data. So it's just a construct on top of it. Now the image channels, when we get them from the image processing library and then convert them, they're in the wrong order for what the neural networks that are trained prefer. So instead of having like the height, width as your index and then your color channel, we need to have the color channel as the first index of the tensor, and then the height of the image, and then the width. Because it's in PPM format, the value for like red, green, blue is from 0 to 255 as an integer, but PyTorch needs it, and most image processing networks, sorry, maybe not processing, but image classification networks need it to be a float between 0 to 1. So that's why we divide every pixel value by 255. Now, to look at this data a little bit, to get some idea of why use stratified sampling, is if we take the different classes, so they've labeled their classes from 0 to 61. Anyhow, I don't know what their signs really mean. I tried looking at them, but I got confused for some of them. So some of these, like this one here, only has 6, or maybe it's this one, only has 6 training examples, and the other one has, over 350. So it's very unbalanced. So that's why I decided when I was splitting this data set to use the stratified sampling rather than throw them all together and do a uniform random sampling. So before I talk about this method for stratified sampling, we can see what the signs look like. So class, I got to scroll down here a bit. I used matplotlib to plot an example from each class. So just the first image from each class. So this is class 0, class 1, class 2, and so on. Let's see if I can scroll over here. So notice a few things here. You have to keep in mind, because some of the tricks we do for data augmentation or other processing steps may or may not be applicable. So you see, if we would flip this one around this axis here, so just flip it, it would look approximately the same for this one, so on. But problem is, if we flip this one, it will look like class 4. So really I don't do any flipping in that direction. Sorry, I forgot which ones. I think this is, and same thing with, if you flip the bottom to the top, then the sign's upside down and there really aren't any, except for maybe this one that makes sense. So just to keep things simple, we don't do any of those manipulations. However, there is some rotation, so we'll do some small amount of rotation. The other thing we can see is some of them are relatively clear, like this image, and others are not. So I do some data augmentation to blur some of the images a bit. So notice the classes are rather varied, and maybe some are more challenging than others, like trying to distinguish these two classes, or maybe any of the parking ones, or this one where they look about the same, but one has a line through it. And also, if we did grayscale, maybe class 59, depending on what you had, might look somewhat like this one, although if you picked out the shape of the sign, they might be distinguishable that way. This one here is 2 images from the same class, but I want to show that if I only look at one example from each class, the color looks pretty good for most of them. However, actually take the last image in this one class, there's not a lot of color. So overall, I think it was a somewhat challenging data set. They're not all crystal clear images. So over time, with machine learning and deep networks and so on, people have started to think more about how to better keep the results reproducible and be able to work with other researchers and get approximately the same results. Or, if you give an example out and you want all your students to get the same answer. So randomness could play a part, but because we're doing pseudo-random, if we set the seeds all to some value, I just picked this number that looks kind of like today's date, then if we reset it each time to this, you should get the same results, because the pseudo-random numbers are deterministic. If you use actual random source, then yeah, all bets are off. So I'd like to talk a little bit about the stratified sampling. If you remember, that's because some classes have less than 10 training examples and some have over 300. So I'd like to, when I split this training set, I'd like to have the validation part, or the, as Angie Ning calls it, the dev test set, be approximately representative of what's trained on. So if there's 10 training examples from class 1, then they might have break them to 90% and 10%, and you'd have 9 to train and 1 to test. And if I have 300, right, then you'd have 90% of 300 in the training and 10% in the validation. It's mostly to make sure that I have at least 1 example from each class in the validation set. And the reason I didn't use the test set for this part is that if we want to compare how algorithms work at the end, then I'd like to test on data that hasn't been seen before. So if we're using it during the training, then in some sense, we're kind of cheating a little bit. So this function, not that interesting, it just is one very simple way to do stratified sampling. And this function will take the indexes that came from the previous function, so I'd pass it in here, and take in our training images and the labels for them, and then it will split this data set, the images plus labels, based on the input indices here. And so what I have is, once we did the stratified sampling, there's no need to keep the classes separate anymore. So this is going to just put everything from the training set into one list, and same thing with the dev test set. So all the labels are in one list, and the image examples are in another list. So those are the functions to actually do it. Before we start doing any sampling, you reset the seeds and get up how many training examples there are for each class, do the stratified sampling, and then split the data set. Oh, I was trying to see how to best present the torch concepts. And at this point, maybe because we were talking about the training data set already, it might be good to talk about using a custom data set class. And I did that for 2 reasons. One is the way the images were loaded. They're all in memory. At least in the past, a lot of the torch data loaders for images would always wanted to read the files from disk. So there are some other tricks you could do, but this is actually faster than those in terms of less code and explaining it. So we pass in the images in memory and the labels, and then transform, which will explain more about those in the next step. But that's to initialize this class. And then in order to this to be used, the data set needs to support the length operation and to get an item from the data set. And the get item is where you can apply the transform if you like, right? So if they're random, then this is where some of the randomness can come into play, because if the transform has some random aspect to it, then each time the get item is called, even if you call it with the same index, you get a slightly different image. Okay, I just keep an eye on time here. So one of the things we have with transfer learning is that we have to take into account how the networks were trained. And there's some way the networks were trained for PyTorch several years ago, and they've lost some of the information on why. But in order to use the pre-trained networks, you have to normalize the images based on the mean. So this would be the mean for the red, green, blue, right? And then here's the standard deviation. The other thing we need to do is make sure each image is 224 by 224 pixels. And the one I happen to pick for the network, it doesn't have a sliding window, so we have to scale each image to the same size. So we do that by torch vision transforms. And so the normalized, you pass in the mean and the standard deviation. And then for resize, it's going to take the image, whatever size it is, and this is what you get back, the height and the width, and it's going to use the bicubic interpolation method for either increasing or decreasing number of pixels. And then I played with a number of rotation or transformations for data augmentation. So this value is in degrees, so each image can be rotated up to 10 degrees. That's not too much, but it gives a little bit of noise. And then you can add some blurring at random to the image. So, Gaussian blur with 0.1 is not so much, you barely notice it, but this gets fairly blurry. But still, if you look at the image, a human would be able to pick it out quickly. So this idea of compose means you take all these transforms and then we can just apply it with this one object. We'll apply all 4 of these at the same time in this order. Because they want to be able to, if we used it with other learning methods, be able to validate in the same way. I didn't apply the data augmentation to the validation sets. So what we can do then is take this, because this is an object that will apply the transform now, and pass it in up here when we create the data set. So that's we pass in the training images, the training labels, and the training transform. And then when Torch will get an item out of that data set, it will apply the transform, which is this here. It'll normalize the image, resize, potentially rotate it up 10 degrees, and add some blurriness. And so we create the training data set object here and the validation one here. So that's primarily how Torch handles a data set for images. I'll switch topics a little bit and talk about how we can use a GPU with PyTorch. So by default, if you're using a notebook like this, or even on your laptop or another machine where you're typing in your code through your editor or your IDE, and then you run it, or you run it from the command line, Torch is going to run on the CPU, whatever's running that program that you started. So doing this, saying that the device is CPU, it really doesn't gain much, except that now we can abstract something. So if this is just, I can ignore this for our purposes here, but it was just if we want to switch the notebook in real time or going through and run it again. Then if you didn't have the right runtime here, wasn't selected, then, and you want to use the GPU, as we saw with Sona showing it inside Torch, instead of calling it GPU, it's called use Cuda. So that's our device, right? Torch.Cuda, because it's based on the NVIDIA cards. So if I go up here, right, in notebook settings, if this was none, then you try to say, is Cuda available? And it will say no. And then I just have it raise an exception so people would know that they have to go back here, change the notebook settings to GPU and then run it. So right now, after we execute here, we're using the GPU if we use this device. And the reason I did that in this way is that when we start using some of our ideas now, then we'll have to explicitly ask for the tensors to go to the device. So in order to train a network, we need to have a way to sample the data, right? A lot of times they call it mini batches, and you might do train on 32 images at a time for each iteration of the back propagation, optimization, and so on. That concept in PyTorch is a data loader for images. So I have one data loader for a training set and one for the validation set. Because the order of images may matter if you train them all in the same order and you end up having your data set sorted by class. Maybe you don't want that if you're doing mini batches. So we just shuffle it. PyTorch will randomly shuffle it. For the validation step, the way I have that, it validates all the images in the validation set, but batched. So there's no need to shuffle because that step is going to validate everything. And this is just an example code to show that, if I create, or I take a sample from this loader, the first batch, is it on the device? No, because it's false. Is it pinned? Yeah, because I said pin memory. Okay. Then if we send it to the device, which up above was set to the GPU, then you check that and oh yeah, it's actually true that it's on the device. And then just to be explicit here, the device is the first GPU. So Eric, how much time do we have left?
We have until 8, so we still got time.
Still got a little bit of time. Okay. Yep. This is where this function is where the main, I don't know if work is what you want to call it, but the main learning loop is. And the reason I use the function is that you could change any of these parameters right without having to rewrite the code. So the epochs is the number of times you go through the training set. The model is the model you want to train. Your loss function is what type of loss function you're training with, optimizer. And then the 2 data loaders we had above is what we'll be passing in. So, and then which compute device. So I'll try to go over this fairly quickly, but if you have a question, do feel free to stop me. This part from here, where it starts the epoch and starts with model train to this print statement, is training. So that's, you can train in just a few lines of code with PyTorch. Of course, you had to define all this other stuff before, but so the model, you set it in training mode. You want to do evaluation or validate the model, and you set it in evaluation mode. So this epoch is going to go through all the images in the training set, but do the mini batches. We set it to 32 at a time. So send the images and their labels to the GPU, and then this function's down below, but it will basically take the model and do one step for the mini batch of the optimization, and then compute the loss and give that back, and then keep going through the loop. And this is optimization steps in here. So after we do that many, then we just, to see our progress, we can check on the validation step, which is down here. So the training loss, because it was averaged, you just multiply by a number of examples and then take the entire loss and just take the average. Now for the validation, I left the note up here to say what this means, but whenever you have model and evaluation mode, you still have to tell it to not update the gradients in the model parameters. Otherwise, it still wants to do that. So even though the model's in evaluation mode, we don't want to update the gradients. And this is kind of a magic trick, but we can ignore that for now rather than writing in a loop like this. And then it just depends, or get the loss for this epoch on the validation set. And it was, the goal is right to minimize the loss function. That's what we're optimizing for. See if I want to go over this or not. I'll go over this fairly quickly, but so in the, here's where we call it, right? It's one optimization step. I use the same one function for the validation, but because optimization is none, it's going to skip this part and just do the loss function. So what we do for the optimization is compute the loss function based on the current model parameters and the labels. And then, so say we're training, the optimization won't be none, it'll be some object. Then you do backwards propagation of the loss through the model. So I saved all this, right? The stuff is still saved, so we'll be fine. So once we compute the back propagation, then what needs to happen? Then your optimizer needs to tell you which direction to move. So that's what the step is. You make some very small step in directions to reach your optimization goal. And then you want to zero out the gradients each time we do that. So for transfer learning, this is a small network. So you could probably run it on a phone. Even now, maybe your iPhones are big enough, powerful enough, and have enough memory that you could run a lot larger net. But this one's very small. It's, I think, 2% the size of AlexNet, something like that. So the number of parameters is very small. So what we do is import this model. So PyTorch has about between 10 to 15 trained models for image classification. And so this was one of them. You just go to torchvision.models, and then there'll be VVG 11, blah, blah, the Google Net, the Inception 3, and so on. And then if you set pre-trained to true, it will download the weights. And then you can, because they overloaded the print value for this, right, or how the description of this model, will show you what it looks like. So I don't have time to go into all of them, but this is where it feeds in. So you get a convolutional network, then a ReLU max pool, and then it fire with all these in it, and so on. So this net, it's still considered a deep network, but it's not that big compared to any of the other ones. So there's still, I think, if you consider these as layers, there's still like 12, 13 layers. Then the last layer is the classifier. So it will do this in sequence. It'll drop out and then do convolution and so on. So this is the part where we wanted to, instead of doing 1,000 classes is what it was trained on, want to do the 62 classes for the signs. So that's what I do here. So right, I downloaded it, called it squeeze_net. So I'll rename it as model net. And then we're doing transfer learning. So the weights are already pre-trained. We want to make sure they don't change. So go through every parameter in this network and set requires gradient to false, right? Then replace the classifying network with one that has number of classes, which was 62 instead of 1,000. And so because we replaced this, by default, it already has the gradient set to true, that it requires the gradient, so we don't have to set that. There's some details that I'll gloss over, but in order to, forget which one of these, but in order to set it and tell it that there's 62 classes, we also need to set the number of classes to that. And then I want to send this model to the GPU. And in the next step, it shows how to train the model by calling that fit function. So the optimizer, based on Andrew Ning's course, this optimizer works fairly good, the Atom optimizer. It might be old now, but as of about 5 years ago, it was considered about the best choice for most applications. So for PyTorch, you have to pass in what parameters can be changed. So for our case, it's only this set, which is doing the classification. If you were training the whole model, you might pass in the model.net and all the parameters. We don't want to move very fast at all. So the learn rate's pretty small, and this epsilon is very small. So it only takes very baby steps, right? So, and there's some decay in it too, which I won't go into now, but you're not always taking this step. Over time, the step gets smaller and smaller. This is what you're starting with. So what I did was I trained this for 25 epochs. So we go through the training set 25 times, right? And each time it will compute the training loss and the validation loss. So to do that, again, we call that fit function. I went over the main training loop, pass in the number of epochs, this model network, right, which is the squeeze net, but the only parameters we're updating are the classification ones. All the image recognition stuff is the same as what was trained, the pre-trained ones. The loss function, the recommended loss function for multi-class is typically cross entropy. So that's what I've used here. I forget, it's a combination between softmax and one other one. Then the optimization, again, is our Atom optimizer. And then we pass in the data set loader for a training set and the validation set and tell it to run on the GPU. And I printed these here, but we can look at these on the graph. Might be easier. So if I, oh, looks like it maybe didn't get that far. Shoot. Okay. So the time to fit still took a while with the GPU. I have to think, can't do the math in my head, but say it took 15 minutes, maybe not. So with the CPU, it takes at least 10 times longer than that. So there is some benefit to using the GPU, even if you're just running on a weak one in at Google somewhere. So if I scroll up, you see the training and validation loss was fairly high at the beginning, and which is what we want to see, that it keeps steadily decreasing. And we could keep going, but this, I ran for more than 25 before and then just cut it off at this for this notebook, because much past 25, like 50, 75 epochs, it wasn't seeing much better. So it's probably overfitting at that point. So I can skip over this part just to get to the accuracy. So because we were testing it based on the validation set, we maybe expect that we get a higher accuracy, but still 87% isn't that bad for this squeeze net. It actually gets a lot less than that on the image net. So overall, I think that, you know, this is a good, I don't know if you want to call it a toy problem. This is a good way of seeing how you can apply transfer learning to a small data set, so that you don't have, that you can take all of the image recognition that was trained into that network from ImageNet or some other huge image data set, and then apply it to your problem that maybe has a lot smaller set of similar images, right? So I think if we looked at, I hope I have the data set right, that is called ImageNet, but you look at that data set, then it's not that much different, the images, from things like this. Maybe if you had some really complicated images, yeah, then you'd have to find a different data set for transfer learning, or you might have to actually train the whole model yourself. Okay, with that, sorry I went over a couple minutes, but if there's any questions, I'll be happy to answer them. Otherwise, thank you for your time.
All right. Any questions for Jeff and Sona?
Eric, I think there was a question on the chat asking about the notebooks being made available. We will be making the notebooks.
Mm-hmm. Yep. So yeah. So I think just email Justin, and then Justin will share with the attendees.
Okay, sounds good.
Yeah. Questions, comments? All right. On behalf of the AppliedAI community, Sona and Jeff, I want to say thank you so much for sharing your expertise and time with us this evening. The attendees, I also want to say thank you so much for sharing your time with us this evening. We appreciate it.
Yeah, thank you for having us.
Yes, you're welcome. You're welcome. You're welcome.